Hello, everyone. Thank you so much for joining us today. Let's welcome our speaker, Feng. He is currently a second year PhD student in the CC department at the University of California, San Diego, advised by Professor Jingbo Shang and Professor Vish Krishnan. And today we have him here to present his amazing work on DenseMixer that basically improves the post training of mixture of experts. Feng, it's really privileged to have you here. Before we begin, just a quick check. Are you all set at your end? Can you please check if you have the screen sharing option available?
Okay, sure. Let me quickly check that. Okay. Thank you. Thanks for the introduction and thanks for having me. Thank you for everyone for coming. This is Feng. Today, I'm pretty happy to share our latest work on the DenseMixer, improving MoE post-training with precise router gradient. So this is a joint work with my collaborators at UCSD and Microsoft. So this work is still in progress. So the results are pretty fresh, and some of the slides may not have been well polished enough. So feel free to interrupt me if you have any questions during the talk. I'll be happy to answer that. Okay, let's get started. So as large language models keep scaling up, MoE, or the mixture of experts, is becoming the dominant architecture among the top tier LMs. So for both private and open source models. So actually, this slide was made just 2 weeks ago when I gave a talk at the Quentin. So now after 2 weeks, so for the open source models, we have Kimi K2, which has 1 trillion total parameters, and the Qwen3 coder, which was just released yesterday, and it has nearly 500 billion total parameters. So both of them are MoE models, and they're extremely good and exciting. So compared to dense models, MoE are more efficient for both training and inference, but it is also much harder to train. So for example, for the Llama series models, they are pretty successful earlier, but the newly released Llama 4 didn't live up to people's expectations. So we can know that, like, even for the LM masters, like the Llama team, we also encounter some new challenges when training MoE models. So you may want to ask, what's the difference? So if we take a closer look at them, we can find that MoE and dense models, they are almost the same in architecture. The only difference is that MoE has something called router. So that means for each token, the router determines which expert to activate during the inference. So it is safe to say router is the cornerstone of MoE. So therefore, we propose to improve MoE training from the router perspective. So for the rest of the talk, I'm going to cover the following aspects. And first, what's the problem of MoE training? So most of the MoE models adopt the implementation of the TopK router, which basically takes a continuous representation as input and outputs a discrete expert assignment. Here, since we introduced a discrete variable, the computation becomes non-differentiable anymore, which directly affects the calculation of the router gradient during backward propagation. To be more specific, the MoE forward pass contains the following steps. So here I'm going to introduce a couple of equations, but they are only for describing the training problem more precisely and not for complicated derivations or computations here. So first, we compute the routing weights, which is just a softmax distribution over the different experts here. It is basically implemented by a linear layer or something and apply a softmax there. So it's pretty straightforward. So second, we compute the expert output, which is just a weighted sum of the activated expert's output. So Pi here is the routing weights we just computed. And finally, we compute the loss using some loss functions. So far, everything is good. But please notice that here we introduce the TopK operation, which will affect the following computation during the backward pass. So to make it clear, I put the follow pass here in the box. So now we want to backpropagate through the final loss L to the router parameter theta. So which means we want to calculate the router gradient nabla theta here. And we can expand it using the chain rule, and we can further expand it to the right side. So here, the first term on the right side, partial L, partial Y, and the last term, partial pi and partial theta. These two terms are both differentiable, so we don't need to worry about these two. But the middle term, the middle blue term is non-differentiable because of this TopK operator is not defined here over the partial Y here. So the calculation of the entire router gradient is not straightforward. And the non-differentiability of the TopK router is one of the key reasons why MoE training is so hard. Any questions so far? Okay, so let's continue. So actually, maybe you want to argue that you didn't encounter such like a non-differentiable issue during the conventional training of MoE. Maybe you can smoothly backpropagate without any issue. So what's actually happening here? So this is actually because during the MoE forward pass, when we compute the final output of the MoE layer, we actually multiplied the expert output by their routing weights. It's multiplied by this like the 0.05. So such multiplication somehow just included the router into the computation graph. If you don't do this, the router is not even in the computation graph, so you cannot do backpropagation. So since we included in the computation graph, and the PyTorch autodiff mechanism will automatically compute the gradient for this part. So essentially, such conventional solution is just to directly backpropagate through the activate experts only. While our proposed method, DenseMixer, is backpropagating through all of the experts to get a more precise router gradient estimation. So this is fulfilled by a trick called straight-through. Then what is straight-through? You may want to ask. So recall that the TopK router introduces some discrete variables, and then thus making the entire training process not differentiable anymore. So straight-through is a method to estimate the gradient of the discrete variables. So for a non-differentiable function, straight-through treat it as an identity function during the backward pass. So for example, we have a discrete random variable from discrete variable D, which is a one-hot vector calculated by the TopK operator. So the operations on both sides are differentiable, but the middle one is non-differentiable, and we cannot directly calculate the gradient here. So we don't know what's the value of the gradient here in the middle. So what straight-through does here is that during backpropagation, it treats the middle term, it treats the gradient of the middle term directly as 1, or identity matrix more precisely. So which has the same effect as like applying an identity function to D. So when implementing this in PyTorch, the pseudocode is like this, where the p theta D is a continuous value after the softmax, and the D here is a one-hot value. So in this way, straight-through can successfully approximate the gradient of the TopK operator So mathematically, the most important part or the most important problem in MoE training is to deal with the middle blue term because it is non-differentiable, and then we want to approximate the gradient here. So conventional method or the conventional solution accidentally treat it as the I times TopK pi I, while DenseMixer treat this as a middle term as an identity function. So using the straight-through approximation. So the final format of the router gradient is also different, showing on the right side, where the conventional method only backpropagates through the TopK expert here. Since here we are summing over the TopK experts only, and while the DenseMixer backpropagates through all experts for more precise router gradient estimation. But it also comes with a side effect here. So DenseMixer requires the output of all experts, which means compared with conventional method, we need to perform an extra forward pass on those inactive experts so that we can obtain their outputs. But actually for post-training, there's a trade-off between efficiency and performance. Different than pre-training, post-training has the following three characteristics. So first, we have much less data during post-training than pre-training. And second, we care more about the downstream performance, and that's the reason why people trying so hard with different types of compute scaling after pre-training. So you can imagine how hard it is to improve the performance on certain benchmarks. You may need to filter hundreds of thousands of high quality data samples to achieve that. Third, we find that the efficiency is not the top one priority during post-training. So for example, a lot of people just directly utilize the Hugging Face models for post-training instead of implementing a customized group GMM kernel. So most people still using the slower implementation provided by the Hugging Face transformers, which uses a for loop implementation. So this all indicates that for post-training, we probably can endure some trade-offs between the efficiency and the performance. So our DenseMixer method can be summarized as it provides more precise router gradient estimation at the cost of an extra forward pass on those inactive experts. So please notice that the extra computation only happens at training, and it does not affect the model inference at all. So we are actually trading more compute for better performance here, and we think this is acceptable for post-training. Any questions so far? Okay, great. Next, let's see how much improved.
I wanted to ask one thing. Are we using the inactive experts only for the gradient calculation, or do they have any effect on the output calculation during the forward?
During forward pass, we just compute the output. We don't use it for the final output. So the forward pass is still the same. We didn't change the forward pass.
Thank you.
Okay. Okay, let's move to the next part. Let's see how much improvement DenseMixer can bring us, and also how much overhead the extra computation introduces actually. So we conducted experiments in the post-training setting. So we started from the base models without being without being instruction fine-tuned already. So we specifically we selected like 3 base models across different scales. The total parameter ranges from like 7 billion to 30 billion, and their active parameter ranges from 1 billion to 3 billion. And we have different architectures. The middle one adopts the shared expert, just like the DeepSeek V3 model does. And they also support different context lengths and using different implementation tricks, such as the normalized TopK probability one. So only the last model uses this trick. And these models are actually pre-trained with different training recipes. I mean, this is during pre-training stage. The 7 billion and the 30 billion models are actually pre-trained from scratch, and the middle one is the middle 14 billion model is actually pre-trained from upcycling. So for the first two models, as they are released pretty early and does not support super long context, we just use some conventional instruction dataset to train and test them. But for the Qwen 3 MoE model, we conducted experiments on long COT datasets and evaluated on the challenging reasoning tasks. So we mainly compare with three baselines here. So the first baseline is what we just introduced previously. We call it conventional method, which is kind of like the standard way or the default way to train MoE. The second baseline here is ESFT, which is expert specialized fine-tuning proposed by DeepSeek AI. And then the last, frozen router. This is suggested by some open source training frameworks. And because the intuition is that the training MoE is so hard, the router is so fragile, we better don't train it at all. So for those who doesn't know like too much about the ESFT method here, so it's actually a kind of parameter efficient fine-tuning method, which before the training stage, they calculate some importance score and determine which expert to update. And during training, they only update these experts to maximize their expertise. So for the first two small-scale MoE models, we consider the two scenarios here: full fine-tuning and lower fine-tuning. So as for the OLMoE model, in most cases, DenseMixer outperforms the baseline significantly. And it's worth noticing that in both full fine-tune and the lower fine-tune, frozen router sometimes outperforms training routers. This is a little bit surprising, indicating that for the router, learning is not necessarily better than not learning in some cases if you use the conventional training method. And for the Qwen 1.5 MoE models, we conducted experiments in the same setting as the 7 billion models. And the results here are pretty consistent as what we have seen on the 7 billion models, that DenseMixer is almost better than the other methods in different settings. And similarly, we also observe that the frozen router here can sometimes be better than training router. But in contrast, training with DenseMixer is always better than these two methods. So one thing to mention here is that we didn't spend too much time fine-tuning the hyperparameters and cherry pick the best performance for our method. So actually, how we did it is when we conduct the experiment, we first do our grid search on the hyperparameters for the baselines, especially for the full fine-tuning baselines. We grid search on the batch size and the learning rate, and we find the best one that yields the best performance for the baseline. And then we just directly adopt these hyperparameters for DenseMixer, and we seamlessly get the better performance here. For the Qwen 3 model, we use two datasets for training. The first one is the Nemotron code dataset, which is a subset of the NVIDIA's just released the Llama Nemotron's post-training data. So because we're doing long COT here, we use three different sets of decoding hyperparameters to minimize the evaluation randomness, because we can see that even for the same model or the same checkpoint, if you use different decoding hyperparameters, the performance is different. So we don't want this such randomness to disturb us or leading us to some false conclusions. So for the same, if we look closely at these results, for the same set of decoding hyperparameter, DenseMixer consistently outperforms the baseline on different benchmarks and the overall performance here. And secondly, we use the Stanford S1 dataset, which only contains like a 1K training examples. And we tested on the math and the reasoning tasks. Similarly, we observed that DenseMixer is also outperforming the baselines in most cases under the same decoding hyperparameter. So since we have already seen so much gains in the performance side, we must pay some price for the efficiency side. So on the efficiency side, for training flops, we compared to the conventional method, the DenseMixer only increases the flops in the FFM part. So let's take the Crane 3 30 billion as an example. So the upper part is for conventional training, and the bottom part is for DenseMixer training. So we can see that for DenseMixer, the increased flops is only happens at the forward pass, because we don't do extra back propagation through those inactive experts. And theoretically, compared to conventional training, the DenseMixer only introduces like 46% extra flops here. But in the actual training, there is other overheads like the communication. So the extra time consumption is much less than the theoretical value. So in our experiment, we use the Hugging Face model implementation. So the bottleneck is still actually lies in the kernel implementation. So reflected in the training time consumption, DenseMixer is not that slow. And we currently have an optimized version of the implementation, which is almost the same speed as conventional method if you use the Hugging Face model. And we will release this implementation after we finish the internal testing on the performance side. So finally, let's look into some implementation details. Yeah, though it sounds like pretty straightforward to apply, to directly apply straight-through to train a router. And we actually spend a lot of time to make it work. So first of all, we have released a plug-and-play implementation of DenseMixer as a pure API package. You can easily install it with pip install DenseMixer seamlessly. And if you're using Hugging Face model for your original training, you don't even need to change your code to use DenseMixer. You just need to set the environment variable, and it will apply the DenseMixer directly. And welcome to try it. So for more technical details, we find that one critical issue is that where to apply this straight-through. So basically, there can be two ways to implement this in code. So one is to apply this at the routing weights, and the other is to apply at the gating mask. So both are mathematically correct, and you can do the derivations smoothly from the left side to the right side. So if you do the derivation, you probably can get the router gradient as the right hand side. So for these two formats are so if you do the derivation, you will have these two formats, and this is mathematically correct, and you can implement this. So the only difference here is whether you times the pi I here outside of the top K pi here. So because the upper side of top K pi directly give you the top values in the pi distribution. And we actually tried both of them during the experiments, and we find the first one works better. even though we think that the second way to implement this is more elegant and more smooth, but it didn't work actually. But it didn't work universally. So we actually got but indeed we actually get some very good results on the second one, especially on the mathematical benchmarks, using by using a trick called temperature scaling. The results are actually much higher than the numbers we are currently reporting. But since it didn't work universally, we leave it for further exploration and didn't report the results here. So there's another complicated case to handle. So recently, there are a lot of MoE models adopting the normalized TopK probability implementation, which normalize the routing weights after the gating side. So please note that all the previous derivations are based on the earlier on the easier case, and we did not touch this part in the previous slides. So in the normalized case, the only thing different is that the final for the final output y of the MoE layer, it becomes the term in the bottom side. So which has the TopK operator on both the numerator and the denominator. So this actually makes it harder to estimate the gradient of the router if you do the calculation here. Because we are approximating both the numerator and denominator, and since mathematically this will introduce some extra computation, so which makes the estimation not that precise anymore. So we have reached a temporary solution by treating the TopK and non-TopK parts differently, but we don't think this is a perfect solution. It's kind of decent and works well, and but you can check the details you can check more details in our blog and the code implementation. So what's beyond DenseMixer? There's some other ways to approximate the TopK router gradient, such as reinforce, reinmax, and sparse mixer. Because you can find that all the change here is we changed the gradient approximation of the non-differentiable TopK operator here. So for these three or other methods, they can also provide better estimation of the router gradient and thus benefit the training here. So here I show an example of the sparse mixture case. So this case is actually under the pre-training side. So during pre-training, the two curves are for conventional pre-training and pre-training with sparse mixer. We can clearly see that sparse mixer is doing very good without, and also it does not require the model to be densely activated during the forward pass. But such method requires sampling, which is challenging to implement if you implement this in code, and it is also not compatible with existing MoEs. So what I mean here is so for the sparse mixer, it usually works for like one or two active experts, which means you can use top one and the top two so that you can do sampling by sampling the top one expert and sample the top two experts without replacement. But no more than that. And the current MoE models are usually using fine-grained experts, usually have like over 100 or 200 experts and activate more than 2 experts. Usually they activate like 8 experts or 16 experts or even more. So that's the reason why we feel excited about DenseMixer, because DenseMixer is very easy to implement and works well on existing models. Okay, so for the final takeaways, first, DenseMixer trades speed for performance, and it's reasonably slow. It's not deadly slow. And second, we find that the precise router gradient really helps post-training. So even if the model is pre-trained using some imprecise router gradient. And finally, we want to know that the router is always the key to optimize the MoE training, because other parts are just the same. It's nothing new. It's pretty similar to the dense models. Yeah, thanks for listening. Yeah, please feel free to ask any questions if you have. Thank you.
Thank you so much, Feng. We really appreciate you taking the time to share your amazing work with us. Now we'll open the floor for questions. If anyone has something to ask or discuss with Feng, please feel free to raise your hand or drop your questions in the chat.
Yeah, I see one hand raising.
Yeah, Pavan, please go ahead.
Oh, hi. I was wondering why we needed like two separate forward passes, one for the TopK experts and one for the other ones. Like, couldn't you just do it all at the same time? Could you go over that again?
You mean for the computation? Let me go get the slides here. Do you mean here?
Yeah.
So actually during forward pass, it is implemented all together. We didn't do a separate forward pass. So previously, you can imagine that for the usual MoE inference, we are selecting the top K. Usually K is less than the total number of the total number of experts. You can imagine that during forward pass, we are activating all of the experts for each token. So it's not implemented separately.
Oh, okay. So I just see that it says like requires an extra forward pass on inactive experts.
Yeah, it's actually we do this comparison
Oh, I
between
see.
DenseMixer and the conventional training. So there is an extra forward pass on the inactive experts, because for the conventional method we don't do the forward pass on this inactive experts. Yeah, thanks for the
Okay.
question.
Mhm.
Yeah.
Yes, Ganesh, I guess.
Yeah, thanks for your talk. Just a general question. Do you have any plans to test this at scale with bigger models, higher parameters?
Yeah, we want to test that, but honestly, we don't have that many GPUs. As you can tell from the experiment here, I can actually tell you like how much computer you require or how much time you need. So for each of the, so for the 30 billion base model, for the 30 billion experiments, we actually finding that the training is faster than evaluation. So which means because when we do the evaluation here, we want to get some fair results. So when we do this long COT evaluation, we actually do repeating over the repeating over the evaluation samples, and then we are using 32K generation lengths. So for each of the benchmark here, for each decoding hyperparameter, it takes like 4 hours or even more to by using 8 H200 GPUs to do the inference only. So if you can imagine, like if we scale it up to even larger models, we will need like multiple nodes or even tens of nodes to do the evaluation only. So this is pretty huge, and we cannot afford that. But fortunately, last time when I gave the talk at the Quinn model team, they're actually trying to implement this, and I'm not sure if they're gonna use it to train their the next generation model. Yeah, but I'm pretty excited to see that if they really use it. Yeah, and honestly, I think 30 billion model is already large enough for like the academia researchers. And we try different sizes, so we can see some consistent gains here. And we have we kind of confident that this will work in the larger scale. And also, most importantly, I think if you consider the recent models, like I can show so as here, we can see that the conventional method is also approximation, and our method, DenseMixer, is also a more precise approximation. This will I think this will become more important if you have even sparser model, which means, let's say right now you have like a top 1 out of the 8 experts, but what if you have total experts of like a 20 or even 100? So the sparsity becomes even higher. So when the sparsity becomes higher, the conventional approximation becomes less precise, and this will amplify this imprecise router issue. So we believe that if you apply DenseMixer in the even sparser model, this will bring you even larger performance gain compared to conventional training. And you can see that for the just recently released the Qwen3 coder model, so it's even sparser than the previous Qwen3 200 billion model. So right now it's actually activating 8 experts out of 160 total experts. Previously, it was like activating 8 experts out of like 128 experts. So you can see the trend that people are still trying to keep the inference cost fixed, but they want to increase the model's capacity. And in that case, we believe the imprecise router gradient issue will become more significant there. Yeah.
Awesome. And then I have one more question. Just in general about like the intuition behind training the router on models that weren't used in the in the forward pass to generate the output. Like, what exactly is the intuition there, and like how is it intuitively supposed to help the router?
So if we want to understand this intuitively, this is also very simple. So you can imagine that for the let's look at this one. So for the router, let's say in this case we have like 4 different experts, and for the router it's basically a matrix which has 4 entries. So if you only use the TopK generation, which also indicated here. So when you backpropagate from the let's say top 1, the top 1 expert, it will only update the parameter of the router in this like the TopK entry. You can intuitively think in this way. This is not exactly as this, but you can tell when you do the backward here, you only backpropagate the top highest the top highest entry of the router, but the router has like a separate entries, and the other non-activated entries are not updated. So, but when you're using like a DenseMixer, you're backpropagating through different experts, and all of the entries in the router parameter is updated. And also, you can also think of it in this way. So previously, when you have the TopK activation, you just directly train it. You don't know what if I activated other experts, what will happen. So right now we provide you the possibility that you can actually know what would happen if you activated other experts. So that will give you more confident gradient or more confident trial when you are trying to activate some of the experts among the entire set. Yeah, that's kind of like the intuition of behind the DenseMixer.
Got it. So like the loss that's propagated back is only through like the output generated by the activated experts,
Yes.
right? So is it
Yes.
just like estimation of like what the loss would have been if you activated the rest of them?
Yeah, exactly.
Okay, makes sense. Thanks.
Yeah. Thanks.
Hi, Feng. First of all, thank you for the presentation. This was really interesting. I've got kind of a more like a question that maybe doesn't have a good answer, but I was just curious if you had any intuition on if this might work in a pre-training setting as well, if your approach would improve if you were doing MoE pre-training for some reason. Do you think that this might improve performance there? Do you have any intuition on that?
Yes, very good question. So we believe this actually helps pre-training, but it's just not feasible to do that if you can afford, because the reason why people use MoE is they want to achieve like a better efficiency. Yeah. So I'm looking for the curve here. So actually, if you're looking for better gradient estimation for the router, you can clearly check this curve So this curve is using sparse mixer. Sparse mixer is kind of like a similar method to DenseMixer, but it does not require the densely activated in the entire models. So if you look at this, so the takeaway here is if you use better gradient estimation of the TopK router, you can have better performance here. So if you look closely at the curve in the beginning section, the G-shard here is basically the conventional method. The G-shard is getting slightly higher performance during the beginning section, but later on, with the number of training tokens scaled, you can see that the gap between them is becoming even larger. So this is tested on the MMOU benchmark, as the MMOU benchmark has a lot of has many questions, and it covers a lot of domains. So it is not easy to get like such big gain if you because we're using the same data. So this gain is kind of like the free ride. So the intuition here tells us if you use precise router gradient during pre-training, it will also help. But the problem here is for DenseMixer, it's actually paying extra efforts or paying extra compute. So we think maybe this is not wise to do that during pre-training. But if you're pretty rich and you don't care about the cost, you can probably try that. But since we have already shown that because during pre-training, the tokens or the data are usually much larger and much more than the post-training side. So we suggest just go directly with the conventional method, or try some other like the DenseMixer or the sparse mixer style method to do the pre-training. And then during post-training, we can probably trade some extra compute so we can get better performance here. And I have a feeling that like for the current open source models, the pre-training the base models capabilities are kind of similar, and people don't directly compare the capability of the dense models. So because some of the capability or the knowledge is not being elicited. So if you don't do post training, so post training is kind of the key to open open the box of the knowledge there. So we suggest you can use like a DenseMixer or some other method to get like a better performance during the post training side. Yeah, that's kind of like the answer to your question.
Thanks. That was really informative.
Yeah. Thanks.
Hi. I had a follow-up on his question actually. So DenseMixer currently calculates the gradients from all non-activated experts. I was wondering if you ran studies where you chose like maybe the top 2K or 3K of non-activated experts. That's kind of like a middle ground between conventional and DenseMixer, and saw is most of the like gradient signal coming from the like top N routers versus the bottom N routers?
Yeah. Very good question. So I'm looking for the equation here. So yeah, if you look at this equation on the left-hand side, I think this is a very valid suggestion, or you can definitely try that, because since the conventional method is actually working, so you can imagine that we have a diagonal matrix here, and we are only calculating the top K of them. And on the bottom side, DenseMixer is calculating all of their entries there. So you can definitely find some trade-off or find something in the middle, because you're actually calculating more like a 2K or 4K experts. So it probably give you better performance than the conventional solution, because it actually give you better estimation there. So if you imagine that, as we just mentioned, in the ultra sparse case, let's say you have 1,000 total experts number, and you are only activating one of them. So you can imagine that the conventional solution, the approximation here is pretty imprecise, and the DenseMixer is kind of precise, but you're you're paying the price of like a 1,000 times the computation in the forward pass. So it's definitely visible or feasible to do that. We don't do the entire 1,000. We do like a 2K, 4K, or 8K, something in the middle. I think that's pretty feasible. Yeah. But we didn't try that. We just want to show that if you do the extreme case, you activate all of the experts, you can get that gain. So, but if you use less, if you compute the K less than the total number, you probably sacrifice a bit, but it's still better than the conventional solution.
Yeah, thank you. Yeah, I was wondering, like, yeah, I thought this method might have trouble scaling to very, very sparse MoE. So that was something I was wondering about. Thanks for your insight.
Yeah, very good point.
If we have no more questions, I would like to ask one. So I'm not sure like if I understood it the right way, but I was just thinking that during the training, as you have mentioned, we are using dense activation and activating all the non-active experts as well. So like it might learn a specific way of all the experts collaborating with each other or a coordination between them. But during the inference, as you have suggested that we do not apply this during the inference, so it would be still sparse or the conventional sort of, you can say, environment during the inference stage. So have you observed any change during the training and the inference time because of the change of this environment? Because as also Pawan suggested, if we can select a few non-experts, the environment would still be very similar to what it would be available at the inference time. But what it is right now, I could see a difference. So I want to know, like, have you evaluated something, or is it just what I'm thinking and it might not be true?
So just want to mention that for during training, even during training, the forward pass is still the same. So we only use the output of we only use the output of the expert to compute the gradient here. We only use the expert output here to compute the gradient. So this is also the reason why it works seamlessly with the existing models, because we are keeping the training and the inference consistent. So which means during training we're using TopK to compute the final output y, and during inference we're still using the TopK to compute the final output y. So I think it doesn't change that much. So it only affects the gradient of the router part. So if you're simply looking at the router, they are pretty different. But during inference, there's no gradient. So I think this also explains how DenseMixer works during inference. So it's actually there's no gradient there, so it's pretty much the same as the conventional method.
Yep. Thank you so much. That answers my question.
Yeah.
Do we have any more questions? I think not. So let's just conclude the session. Thank you so much, Feng. It was a really wonderful session. And sorry, I thought there was a question. So thank you so much. And it was a really nice talk. You explained everything so well and answers the question really well as well. And we'll upload this recording to the Cohere's session, and I'll share the recording with you if you want to share it within your network or something like that. And with that, I think we'll just conclude this session. Thank you again for joining us.
Okay, thank you very much. Thanks for coming.